So recall that if you start with a field k and a positive integer that is other than that is co-prime to the characteristic of field, then uh, and moreover you may assume that the new one, which is the inner groups of units that are inside K star. In that case, you have this short exact sequence of groups. So this is like raising to the power, and this is short exact sequence. And so when you apply Galois homology, let's say H1 you will get so or not H1, so it's apply Planck homology, or maybe you can do a bit better. I think let's not assume this for now. Let's just work with the separable closure. The new one is already inside the separable closure. Now if you apply homology, uh, you will get so firstly we'll get K star. So that is the zeroth cohomology at these two places. Then you have H1 K mu 1, and then you have H1 K this, but this is zero, right? That is Hilbert's map. So what you get, and this map is like is going to expire. So essentially, what you get is basically this is isomorphic to because this is zero. This map is surjective. So that is isomorphic to this modulo the kernel of this map from K star to H1. But that is the same as the image, which is this. So that is what Kummer theory says. Okay. Now, however, you can also approach this thing uh, with a bit more geometric way, right? Torsors. That is pretty interesting. So what you can do is, so let's start with the definition for torsor. The definition is pretty simple. So let's start with the site. Let's start with the size. Mostly we'll talk about etal sites and sometimes FTPF sites, finite diameter. So and you start with a sheaf of groups, or you can also assume it's abelian, although it's not necessary. So this is a sheaf of groups on this side. See. Then a mu torsor, so that is definition. So a mu torsor on the side C is a sheaf of sets script P on C together with left action of this sheaf of groups mu such that so the first thing says that sections exist locally, meaning that for every object in the site C, there exists a cover for which the sections over this cover is non-empty. Secondly, you have this map. So this is like projection in the first component and the action in the second component. So more precisely, if you have GAP will go to P, and this is the action. So if this defines an isomer. So these two things hold, then uh, we call it a mu torsor. So in particular, as an example, you may take P itself as the mu with the action being the group multiplication. So that gives you what's called the trivial torsor. That is called the trivial torsor. And this holds. So there's so, so P is trivial torsor if and only there is a global section. So meaning that, so more precisely, mostly our sites will have a terminal object. So because we will be talking about schemes over a fixed scheme, base scheme, so there is always a terminal object. So over the terminal object, if sections exist, so, so if E is a terminal object, if that is non-empty, then it's a trivial tensor. That's easy to check. Because if you pick such an element, so here E is, let me start with site with a terminal object. So if you start with such an section over the terminal object, let's call it S. Then multiplication by left multiplication by S gives you uh, the required uh, part 1 and part 2 of the definition. And in fact, it will define an isomorphism between mu and script. So, and point 2, by the way, says that the action is simply transitive. Right? So this is says that the action of mu on script 2 is simply transitive. That is obvious from this. And in particular, every torsor is locally true, right? Because locally sections exist. So locally, it looks like isomorphic to the sheaf of groups that we were working with, that means, but that is only local. Globally, if there is a section, meaning over the terminal object, then it's trivial. All. And now, uh, suppose you are given two torsors. So, so by the way, I'm gonna denote a torsor with not only P but also with the action mark. So that is the notation. So this will be my notation. So that is the P that I just said above. And this P is the action mark. So, so this row is the action mark. This that is basically called this. So this is action. Now, if you are given two torsors, this is script P 0 and another one is P prime 0 prime. So morphism uh, is basically a morphism of sheets, basically, such that the obvious square comes. So you start with this. You have uh, this mark, which is row. Then you have F. There you have this row prime, and that is just identity times this has to come. That is a morphism of torsors. So then, with respect to these objects and this morphism, we're going to define the category of new torsors, which will be denoted by let's say torsors. It is the category of new torsors. Okay, so that is actually important because we'll be focusing on the case where this chief of group is just mu. So what do I mean by mu? So let's set up the base thing. So it will be my scheme. N is a positive integer, invertible on x. Then mu n basically assigns to a scheme S all the uh, regular functions that satisfies inequality. So this nth group of the regular functions. So we'll be interested in processor uh, this mu torsors, sorry mu n torsors. That is our central object. And before doing it, so we'll actually define two categories, and those two will be mutually equivalent. And from there, in particular, if you take the scheme to be spec of the field, the uh, isomorphism for. So remember, that is our find the bijection between these two fields. So firstly, what we need to define before doing these final things, that how do torsors get classified by the first coordinate? There is one major thing. So one need to show that the torsors of mu is in bijection with H1 of C mu. So that is the first thing that one needs to show. Okay. So that maybe I will discuss next time, but this is not difficult. And from there, you need to define another category, which is basically the category of invertible sheaves on X, such that the nth power of the sheaves is trivial. So, so that category will be actually equivalent to the movement toss. From there, uh, we need to then use this identification of torsors, movement torsors with the first homology, with that to conclude the Kummer. So that that I will discuss next.